So remember, this is the preview, right? If we treat this as a preview lesson, so we may go a little faster, right? Go a little faster. And we're not going to prove the detail, right? For some concept. We just quickly introduce the concept, get idea of the concept from intuitive way. So then we can do the practice, okay? Solve the problem. Okay, so this chapter have two topics, right? First section is about limits. Let's talk about limits. Okay. So this notes later I can share this with you, right? After today's lesson. Okay, so this is the limits, right? We're going to introduce the limit. So the main objective for limits concept, right, based on AP calculus curriculum is this. Right? Be able to evaluate limits algebraically, graphically, and numerically. Right? Three different approach. If you're allowed to use a calculator, you can do the graphical approach. Otherwise, just do algebraic approach. Okay? Yeah, that's the main objective. When we talk about this concept of limit, there is another two concepts related. You may already learn from AP, from pre-calculus, right? Called asymptotes. Asymptotes. Okay? Yeah. First, let's introduce the concept, intuitive or informal definition of limit. Okay, limit. Yeah. Good. And let's look at example, right, to show this idea. Okay. So let's see. I have this function. Right? You can graph, use a calculator if you don't know how to do it manually. Okay, if you graph this function, what happens? Right? What's the graph? Graph this function. Right? This is a piecewise function called a piecewise defined function. This is something you learned from algebra or pre-calculus. Okay, so if x not equal to 2, if you graph this function, actually, if x not equal to 2, actually, you can simplify this, right? Like we just did. You can cancel out x plus 2, x minus 2, right? If x not equal to 2, you can cancel out x minus 2. Yes, you factor out the top, right? So basically, it's a line if x not equal to 2, right? Line. Yeah, this one. Right, this line. When x equals to 2, when x equals 2, actually function value is what? Is a different. It's not on this line. Actually, it's here. Right? When x equals 2, actually function value equals 1. So that's the graph. So basically, it's a line with a hole, a straight line with a hole. Then plus this point. Okay, that's the graph. Now, question. We're going to introduce the concept of limit, right, using this example. So, okay. Intuitively, limit, right, easy to understand. So in algebra, if you want to find the function value at 2, you just plug in, right? Here, actually, just 1, right? That's the algebra. But in calculus, we're going to talk about this in calculus. How about this? We say this, right? We say when x approaches 2, when x approaches 2. Right? When x approaches 2, what happened to function? Yeah, what happened to function? When x approaches 2. You see the question, right? Totally different, right? In algebra, you just plug in, you just find the value of function at a specific point. In calculus, we talk about the process, right? An infinite process. We want to talk about this. When x gets closer and closer to 2, what happened to function f? But remember here, x gets closer and closer to 2, but never equals 2. Okay, what happened to function value? Okay, we can easily see here. Looks like our graph, right? Looks like a function value, right? Look, if you look at the point on the graph, look like this, right? The point, the corresponding points, right, on the graph will get closer and closer to this point. That makes sense, right? Okay, if you look at the value of a function, this you look at value of y. Right? If you look at value of a function y, actually you can see, did I graph correctly? Let me see. Yeah. Okay. Actually, it's not in scale. Yeah. It's not in scale because this is a 2. This is the 3. So okay, sorry about that. It's not in scale. Okay. Yeah. I can see. Looks like a function value actually approaches 4. Yeah, approaches 4. Yeah, that's the intuitive concept of limit. Yeah, especially if you look at the graph. Is it okay? Yeah. So as x get closer and closer to 2, what happened to function value? What's the behavior of the function value? Okay, so from this one, we say this, right? We say the limit, we say this symbol, right? We say limit of a function at 2. This symbol means limit of function at 2, right? Basically, it says function approaches 4 as x approaches 2. We get 4. Yeah, 4, right here. This value, right? But not 1. Okay, it's not 1. If you plug in 2, actually you get 1. You can see it's different from the value of a function at 2. Okay, remember, right? So the limit has nothing to do with the value of function at that point. Okay, let's summarize. So this is the intuitive meaning of limit, right? Intuitive meaning. So we say this, right? So we assume this some basic condition. We assume functions defined near A. You can see near A, right? Assuming function defined at near A, but accept possibly at A. That means what? That means the function can be undefined, right? It's okay. Function is undefined at A. It's okay because we don't care about the function value at A. We only care the function value near A. What's the behavior near A? Okay, so that's the idea. Okay, so then we say limits of function as x approaches A is L. We write this symbol, right? What's the meaning of this? This is the meaning, right? If we can make f arbitrarily close to L, right? So we can make a function value arbitrarily close to 4, right? We can make a function value, right? Arbitrarily close to 4, as close as we wish, by taking x sufficiently close to A, but not equal to A. Yeah, so that's the idea. You can see, right? As x, by making x sufficiently close to 2, we can make function value arbitrarily close to 4. That's the concept of a limit intuitively. A formal definition, unfortunately, is very complicated, right? It's not part of AP calculus here. Okay, so we don't have to worry about the formal definition. What's the meaning arbitrarily close to L or sufficiently close to A? What's the meaning mathematically, right? Exact meaning. We can use inequality to describe this, but it's not part of AP calculus. We don't have to worry about, right? For AP calculus, just get intuitive understanding. That's good enough. Is okay, everybody, so far for this one? There's a shorthand notation for limit. We can also write down this one. Same thing, right? So as f approaches L, as x approaches A. Exactly the same meaning as this symbol. Okay. That's good. That's the concept. Okay, you can read the textbook or your school textbook, right, for more details about this concept. Is okay? Let's look another one. so far you can see I'm doing algebraic, doing graphically because it's easy, right? Later we'll do algebraic, okay? This one, as x approaches 0. Again, we're using a graphical approach. We need to graph this function. Okay, well, this function, if you're allowed to use a calculator, you can use a calculator to graph this. Otherwise, you just rewrite this, right? So this one actually equals this. It's a piecewise defined function. We know if x is a positive, we can drop absolute value, right? So we get 1. If x is negative, actually, if we drop absolute value, we get -1 because absolute value now change to negative x, right? This one change to negative x, so it's a negative x over x. Yeah, for x less than 0. Oh, so we can graph this function. 0, no, 0 is undefined, right? As 0 is undefined. So it's okay. We don't worry about right function value as 0. It doesn't matter, right? So we can easily see. So if x greater than 0 is a constant function, 1. If x is less than 0, it's a constant -1, right? Okay, so what's the limit? Tell me. Everybody try to tell me what's the limit. If you don't mind, I will just randomly pick some student. It's okay. If you don't mind. Okay, so what's the limit for this one? You guess. Let me ask somebody. Okay, it's okay. I just randomly pick. Okay, so student. How about, let's see from here. Kevin? Yes, go ahead. So what do you think, Kevin?
So I think because there are two, because the lines are separate.
Yeah,
so
thank
like
you. Yeah.
Okay,
good. So looks like a function does not approach a fixed number, right? If x approaches 0 on this side, right? On this side, so we get 1. On this side, we get -1. Which one we pick, 1 or -1? Unfortunately, it's not fixed. If not fixed, right? So then it does not exist. This one example function, right? If you look, right? So from different direction, approach 0 for x, every function does not approach any fixed number. So therefore, is 1. Does not exist. Okay, so it's possible, right? Does not exist. Okay. Now we can introduce one-side limit. Okay, one-side limit. If a two-side limit does not exist, for this one, we can talk about the one-side limit very easily, right? We can say, right, we can deal with the one-side limit, right? We can say this way. We can say the limit of a function as x approaches 1 or approaches 0, right? Approaches 0 from positive side. I put the plus means from right-hand side approaches 0, okay? If I put a plus from right-hand side, means x approaches 0, but x greater than 0. Okay, so then we can say this one, right? So this one actually is 1. It's 1, right? And if we take a one-sided limit of this function, it's a left-sided, right? From left-hand side approaches 0. Actually, we got -1. Right? If a two-sided limit does not exist, it's okay. Sometimes we can, right, talk about one-sided limit, just from one direction, approaches A. That's okay. So that's the definition for one-sided limit. Exactly the same, right, as two-sided, but just from one direction. So we put a plus or minus, right? Means put a plus means from right-hand side. If we put a minus from left-hand side, okay? Yeah. That's the, okay, good. Of course, this is a kind of obvious, right? Two-sided limit exists if and only if both one-sided limit exists and equal. to each other. Yes? So far? Yeah, okay. So if you already covered this, it's okay. Just treat this like a review. So next time we move to calculus, move to derivative, hopefully, yeah, okay. So today we try to cover as much as for limits topic. Okay, yeah. Good. We can do this one quickly, right? Let's see for this one, for the one side and two side limit. Okay, everybody try this one, please. A. Right side limit of f as x approaches 1 is have your answer very quickly. Yes, from here we can easily see, right? Is 1, right? This point, right, is 1. Even though function is undefined at 1, it's okay. It's 1, right? It's 1. Good. B, left-sided from 1, or we can see is 2, right? It's 2 from this side, right? It's 2. C, two-sided, of course, does not exist because they are not the same, right? They're not the same. Yes, if they're not same, one side limit is not the same, so then they are undefined. No, does not exist. We don't say undefined, we say does not exist, right? Let's say D. Right side limit as x approaches 2. Oh, as x approaches 2, right? X approaches 2. Oh, here, right? Looks like point approaches this point, right? So it's a 2. Is it okay? Everybody can follow, right? This one is 2, right? Right side. Left side from this side, right? Also approaches 2. So then f, both one side limit exists and the same, so they are equal, right? So therefore, two side limit exists also the same. Yeah. Okay, that's the concept of concept of limit. Okay, yeah. If you have not learned this, that's good. So now you know the basic concept of limit. Later, when you start right in school, so when you learn this new concept, I hope it will be helpful for you, right, to get better understanding. Okay, now we can generalize the concept limit to limit at infinity, right? Instead of x approaches a fixed number, here we want to see what happens to the function when x just get larger and larger, right? Get larger and larger, no bound. Oh, that's the meaning of x approaches infinity. X approaching infinity means what? X get larger and larger with no bound. That's the meaning. Or you can say x approaches infinity, but usually we don't treat infinity as a number. Okay, so it just means as it gets larger and larger, no bound. Okay, same idea, right? Same idea. So what's the limit equal to L? What's the meaning of this? It means we can make a function arbitrarily close to L by taking x what? Sufficiently large, right? Sufficiently large. Okay. Similarly, you can define limit at negative infinity, right? Negative infinity. Yeah, let's look at this example. Right, again, we talk about the graphical approach, right, to help us easily to understand concept. Later, we'll show algebraic approach. Okay. This graph, everybody is familiar, right? This one, right, is a hyperbola, right? Graph, one of the most basic functions. Right? So we can see as x gets larger and larger, as x gets larger and larger, looks like our function value just get closer and closer, right, to 0. Right? Function value, right, looks like it gets closer and closer to 0. Yeah, but never equal to 0. You can see, right? Never equal to 0, but just get closer and closer to 0. Yeah, so therefore, this limit equals 0, right? Equals 0. Yeah, good. That's the concept at infinity, right? Later we will see the algebraic rule, right, to calculating limit exactly the same, right? As a function limit at finite number. Okay. There's another type of limit we talk about. Still same concept yet, right? So in pre-calculus, if you learned, right, you know. So we say what? If function value at infinity is 0, we say this line, right? We say this horizontal line, this line, right, is horizontal asymptote. Yeah. Okay. If function limit at infinity equals a fixed number, a finite number, right? Yeah. Then we say this line, y equals b, is a horizontal asymptote. Okay, for this one concept. Any question? Yeah, please feel free to ask. Okay, good. How about this one? What do you think? Yeah, if you look at the graph, right? If you have a calculator, you can try it, right, very quickly, or you can use the online graphing calculator, right? So what's the graph look like? This one. Get the graph, then we can find horizontal asymptote easily, right? So let's see. Try it, right? What's the graph look like? Actually, if you use the calculator, you can check, right? So the graph looks like this. See if my graphing is correct. Okay, please try it. As x equals 1, we get 0. X equals 1, we get 0, right? Yeah, right, get 0. I think it should look like this way, right? Yeah. Yeah, okay, you can double check. For now, just use the graphing calculator, right? Because this is a graphical approach, right? For now, later we'll show algebraic approach. Okay? What's the limit? What's the horizontal asymptote? Yes, horizontal asymptote is this one, right? This one, right? As x approaches infinity, either positive infinity or negative infinity, right? Function approaches 1. So our horizontal asymptote is 1. No, sorry, we don't say 1. Okay, we say y equals 1 because it's a line always, right? See this one. This is the complete sentence. Okay, you see that you say horizontal asymptote is y equals 1. Okay, never say 1. It's not correct. Okay, now don't say 1. 1 is number, right? It's not correct, even though it's related to this line, but it's not, right? It should be a line. Horizontal asymptote should be a line. So it's the equation. Okay. So far, any questions? So now we introduce pretty much all the different types of limits, right? The concept is exactly the same. If you know the understand the concept for the first basic case, then the other case involving infinity is very easy to understand. Okay, good. So of course, yeah, you can generate, right, to this case, even though we don't see very often, right? So infinite limits, right? Oh, infinite limit means what? Means as x approaches a finite number, actually function value one just gets larger and larger with no bound. Yeah, right? Function value is now is infinity. Yeah, right? So we can make a function arbitrarily large as we wish by taking x sufficiently close to a, but not equal to a. Yeah. Okay. Of course, you can right generalize to one-sided limit, right? As x approaches a or x approaches a positive or negative. So there are many combinations. Infinity could be positive or negative. A could be plus or minus. So the same idea. Yeah. Let's look at one example. It's very easy to understand. So we just quickly to go over this. Okay. If you look at this graph, I think everybody know log function, right? Basic function graph. Everybody should know, right? Very confident, right? So this is the natural log. If you forgot, you can use the calculator, right? So this is a y equals natural log. So we can see as x approaches 0, as x approaches 0, as x approaches 0, let me write here. Right, looks like our function just gets negatively smaller and smaller, right? So get negative infinity. No bound, right? You can see this side, no bound. So our limit is negative infinity. Yeah, so far, any questions? Yeah, please feel free to ask. Is it okay so far? I hope this way, right? So we approach. So we start with this concept. So then we'll go a little faster. So because we cannot go too much detail, otherwise we'll not be able to cover, right? So I want you just so this is the basic approach. We want to just get a little ahead of your school, so then you can feel more comfortable when the teacher introduces a new concept. Yeah. Okay. Good. So again, we have a so-called vertical asymptote. If we have a limit, infinite limit, we can talk about vertical asymptote, right? So here we say, right here we can say this way, right? We can say if limit at 0 is an infinity positive or negative, so then we can say y equals natural log x. This function has a so-called what? Vertical asymptote, right? Vertical asymptote. So we here is a x equals 0. X equals 0. Yeah, it's okay. So that's probably something you learned in pre-calculus algebra, right? So what's the meaning of a vertical asymptote? Actually, it's related to an infinite limit, right? Related to infinite limit. Okay, good. So here, infinity could be positive or negative. Either way is fine, right? Let's look at one more, right? Look at this one, right? So this one. If you look at this graph, again, use a calculator for now, right? Just graph it, okay? Using calculator, you do the only graphical approach here to introduce the concept, okay? So if let me see what it could look like. You can use a graphing calculator to double check, okay? I think here we have a, this way, right? This is a 2, this is negative 2. When you plug in 0, you get 0. 1x, let me see, 1x between 0 and 2, I got this way. Yeah, that's your graph. Okay, so based on the graph, right, either given to you or you just use a calculator to get the graph. Okay, so what's the asymptote? Here we talk about vertical asymptote, right? Vertical asymptote, we can see. So we have two vertical lines, right? Two vertical lines. As x approaches 2, function approaches positive infinity or negative infinity. Depends on which side, which direction, right? Approaching 2 or negative 2. Okay? So we can easily see these two lines are vertical asymptote. X equals 2 and x equals negative 2. But again, we never say 2 and negative 2. No. Okay, because they are lines, right? They are lines, not numbers. Okay. And last, we don't see very often, right? So we just one special case. I think you may see this when you learn polynomial functions in pre-calculus, right? Polynomial function, the end behavior, right? As x getting larger and larger, actually y is also getting larger and larger. Right? So this is a very special case, right? The limit is infinity, x approaches infinity. Yeah. So basically the graph just look like this, right? Like a polynomial, right? If you look at the example, polynomial function, right? Right? This is the cube, right? Look like a cube root function, right? No, cubic function, right? Polynomial function. You see, right? Function just gets larger and larger as x gets larger and larger, or smaller and smaller. Yeah. So that's all. Yeah, that's for the concept. Now, how do we calculate limit? How do we calculate limit algebraically? That's usually the way we did, right? Traditionally, because with no technology, we have to go through the algebraic process most of the time. Okay, how do we do this? This is the basic idea, right? If we want to calculate the limits algebraically, first we need a bunch of rules. We need, right, a bunch of rules we can use to calculate them. Okay, so what are rules? Fortunately, very easy to understand because kind of quite intuitive, even though we don't give the formal proof or formal proof. Okay, so very simple. Here I just list all of them, right? So in school, teacher may extend, right, the concept a little bit more, show why this one works, maybe give you some more, right, explanation here. But here we just quickly go through this. Okay, very easy. If you want to calculate the limit of a sum, very easy. You just get the sum of each function and add. Okay, so the sum, right? The limit of a sum equals the sum of limits or difference. Okay. So here a could be a positive, a could be a finite number or infinity, doesn't matter. Okay, including limit at infinity. Okay, if we have a constant multiple, actually we can bring out the constant. If we have a product, right, take a limit of product, we just get a product of limit. Again, limit of a quotient equals the quotient of limit. But here, we have to be careful, right? Here is what very important. When we do this, we have to make sure limit of a denominator is not 0. Because otherwise we're dividing by 0, right, on the right-hand side. Okay, then similarly for power, right? If you take a limit of power, you just get the power of the limit. Similar for root. Right? Yeah. For technical reason, we assume a is positive. Otherwise, sometimes you may not be able to take a root. Let's say if n is even, right? If a is negative or 0, sometimes we may not be able to take root. That's why we're assuming a is positive. Okay, that's the 6 basic rules. Using these 6 basic rules together with these 2 simple limits, these 2 obvious, right? These 2 limits obvious. So constant limit, very easy. constant limit is just constant itself, right? Of course, just constant itself, right? Because function never change. As x approaches a, function of course approaches a. That's similarly for this one. Graphically, you can convince yourself, right? If a function is x, of course, as x approaches a, function will approaches a too. Right? So together with these two limits, right? So we can calculate now limits of most polynomial functions, all the polynomial functions actually, right? You can calculate all the polynomial functions limit and some rational function. Yeah, some rational. How? Very easy, just by simple substitution, right? Just simply substitute. Yeah, simply substitute. Yeah. Why? Because of these rules, right? Let's just do one example. Later, you can just simply substitute. For now, we can use the rule, right? Practice using the rule. Later, you can just substitute, right? Let's see. So this one we know. We use addition rule, subtraction rule, a product rule, and the power rule, right? So we get this. I can bring out 5, right? Constant multiple rule, right? Yeah. Okay. To save time, I'm not going to put this here, but you're going to feel the detail later, right? X plus 2, right? Yeah. Because every time I write this, take little time. Yeah. But you should write always. Okay. Yeah. Okay. Then power rule, you can bring out how. Make sure in school, right, in the test, when you do the calculation, make sure show very neatly and completely for each symbol. But here, we just save a little time, right? We don't put that here. Okay, then x approaches 2. Maybe I should write because I want to have a right to be a good model, okay? Yeah, then we can use a basic limit. So this is just 2. So 2 to the 4th power minus 5 times 2nd power and plus 6. Yes, calculate. Yeah, yes. Yeah, you can calculate this one. I think this is a 20 plus 16 plus 16 minus 20 is a 6. If I'm wrong, please correct me. Okay. That's good. So that's how you calculate limit, right? Using these basic rules, right? This for a 6th basic rule. Okay. Similarly for a fractional function. Okay. For fractional function, let's see what time. Yeah, very good. Okay, I think we can cover quite a bit today. So for rational functions, okay, rational functions, same thing, right? So you just use equals, maybe right here, right? Okay. Usually, when you take a test, right, you want to copy the expression, then write down equal. Okay. You can see this is how you show the work, right? This is how you show the work. So you put the alignment here, right, using equal sign for each step. This is the best way, right? Because it's easy to read for people. Okay. Well, let's try this one. So this one we can take a limit, right? Numerator and the denominator, right? Quotient rule. Yes. Right? For quotient rule, right? For each numerator and the denominator, we can use other rules, right? Other rules. So I think now we can plug in because we already know in the part A how to do this, right? Here we just simply plug in. Looks like you can just simply plug in. Yeah, it's okay. So for now, we don't have to write something like this. Okay? Yeah. I think you can follow this. It's okay? So this basically just 2 times -2, right? Over -2 squared plus 4, right? If you use the rule, you should get this. Now calculate this one, you get -4/8 or -1/2. Can I use this rule? Yes, because the denominator not equal to 0, right? Denominator limit is not equal to 0. That's good. That's good. Yeah, that's why direct substitution works here. Direct substitution works for all polynomial functions and certain rational functions. Okay, very good. So now we're going to do something, right, as a little special, right? So it's what happens if we cannot plug in directly? Right? Not all limits can be evaluated by direct substitution. Right? So two other common methods, we're going to introduce another two common methods, right, which involves rational and radical functions. Rational, some rational functions and some radical functions. Okay, so we're going to do algebraic now, right? Algebraic. So let's try this too. Usually when you find limit, you want to substitute first, right? See what happens. If you substitute directly, if there no algebraic conflict, right? It's fine. That's good. Right here, like here, A and B, right? Substitute, then you get a finite number. That's good. How about if this one, if you plug in 2? If you plug in 2, actually you get 0/0. This is not good, right? So the rule doesn't work. The rule doesn't work because this rule, to use this rule, you have to make sure this one is not 0. Okay? If this equals 0, then you see what happens. Right? If you plug in, you get 0/0. Usually this is called the indeterminate form. Later, we'll learn more about this. Okay? When we learn derivative. Usually this is called the indeterminate form. Terminate form. Indeterminate form. What does it mean? It means this, right? If you take the limit, numerator, and denominator, you get both equal to 0. That's called indeterminate form. For indeterminate form, don't say the limit does not exist or undefined. No, we never say this, right? We need to do extra work because if this limit is an indeterminate form, then the limit can be anything, right? Can be defined or can be undefined or does not exist, right? Defined could be any number. So indeterminate form basically means you need to do extra work, right? Extra work, yeah. Okay, do extra work, yeah. Now let's see, how do we do extra work? This is the way, right? We do. So we're going to what? First, we simplify this expression, see what happens. Oh, I assume you know how to do factoring, right? How to do factoring. You see, algebra skills, right? Strong algebra foundation is a kind of essential, yeah, for your success in calculus, yeah. Okay. Then factoring, yeah, it's okay. Then we can cancel out x minus 2. Why we can cancel out the x minus 2? Because x never be 2. We said x approaches 2, but x never be 2. So therefore, these two functions is the same if we cancel out x minus 2. Right? We get this. So our original function, if x is not 2, basically same as this. If am I running too fast, please let me know. Yeah, if you think it's running too fast, yeah. Okay, if you like to a little slow down, please let me know. Or any question, right, you want to have, right, have clarified, please let me know. Okay. So now we can plug in once we cancel out x minus 2, right? Now we can plug in. That's good. Yes. Yeah, Okay, got this one. Well, I think everything so far conceptually easy to understand, right? Even both graphically or algebraically. Until we get here, you may need to, right, have a good algebra skill right here. So for factor, yeah, so here, right, like this. So this is the key focus point, right? So we want to focus on everybody, right? Focus on this key knowledge point, right? How to evaluate indeterminate form. Okay, this one I'm going to skip this one to save time, right? You can try this one. So basically, you factor, right? Factor this, yeah, and you can simplify. It's a similar idea. Okay. Just give you the hint, right? If you forgot. So for this one factor, we need this pattern. So in algebra, we have a few patterns. Right? If you staying right in the class later, I will give you a so-called what cheat sheet or reference sheet for algebra. Okay, so we summarize all the important basic algebra formulas for calculus. Actually, I also have a calculus cheat sheet. Okay, so if you need, maybe later we can share it. Okay. Yeah, this formula, if you remember. Right, if you want to factor this one. Okay. Of course, if here is a plus, I believe here is a plus. It's okay. I just give you minus, right? Plus also works. Yeah. For the other, here we just change to plus. Here we change to minus. It's okay so far. Everybody, so far. Let me know. Okay. Any question or any suggestion? So if you find what will benefit you, right? Most, yeah. Please, right? Give you the suggestion, okay? So I can try to communicate, right, to everybody's needs, okay? Good. How about let's do one more for radicals. For radicals, this one. You can see this kind of a quotient very often. Later you will see why you see this often. You can see here we have a quotient, something, right? Quotient. Denominator is x minus a, top is x cubed minus a, right? Here we have a similar quotient. You can see here. Yeah, this one just square root of 4, which is 2. Here's h plus 4 minus h. It's a secant slope. It's a slope formula. If you look right here, this basically is a slope because top is a rise, bottom is a run. Top is a rise, bottom is a run. It's a slope. Later we'll talk about this more. Right? It's also called average rate of change. Okay, so let's do this one with what's the technique, right? We do, right, for this one. So for this one, we know it's a factor, right? That's the key. Okay, factoring. Very important, right here. Factoring. Yeah. Yeah. For this one is what? For this one, we need another technique. Another technique. You need to, right? So you need to master this technique also, okay, for AP test. Okay, is what is called a rationalization, right? In algebra, you rationalize denominator, right? Here, actually, we rationalize the numerator. In calculus, right? Both common, okay? Rationalize numerator or denominator. Both are very common. Even though in calculus, in algebra, you do only denominator rationalization. Okay, so let's try. How do we do this? Again, let's review the algebra, right? So we do this, we rationalize. So, if we rationalize a radical binomial, right? We multiply what? We multiply a similar binomial, but with the middle sign opposite, right? With the middle sign opposite. Yeah. That's so-called the conjugate, right? In algebra, we know this is called the conjugate of each other, right? Conjugate. We multiply numerator and denominator by the conjugate, right? Yeah. Okay, so then we can use the factoring, right? Factoring pattern. So numerator, we know we use this pattern, right? Is the everybody remember this pattern? Just quickly recall this in case something, right? So this is a difference of square pattern, right? So you square first term, subtract square of second term, right? Let me show one more step. If you already know this, you can skip this step, okay? So then equals, you can see this one give you h plus 4 minus 4 over h. Right? Okay, that's good. So then we can cancel, right? We can, this cancel out, of course. This one we can cancel out, right? So we got what? We got this, right? 1 over. Let's see if it, right, it helps or not, right? Let's see. Oh, I think I should too long, this square root shorter, right? Yeah, right, we got this, right? Algebra, you can see, we, in calculus, actually, you will see, right? In calculus, once you understand the concept, everything else is about algebra. Yeah, you can see most of we do the algebra here, right? Do the algebra. Once we get here, then what? Then we can plug in. Why? Because there's no conflict, right? If you just plug in, so we can, right? We can use those 6 basic rules, right? Plug in. So you can see, look like plug in H. Yeah, that's our answer, right? Okay, for this few steps, any question? Any step is not clear? Oh, by the way, I forgot to ask, right? Everybody can hear me clearly? Yeah, please let me know. If not clear, yeah, please let me know, okay? So I want to make sure everybody can hear, right? Can hear me very clearly. Okay, that's very good. So that's about limits. So today, I think we introduced, right, the basic concept of limits, right? Graphically, everybody can understand, right? Just read the book, if right, for a little bit more details, right? To now, how to calculate limits besides direct substitution, if possible, then we introduce these 2 techniques. Okay, very important. Make sure everyone knows, right? So is the first one is what? Factoring, right? Factoring, if for rational function or radical function, rationalization. These 2 techniques. Okay, for part B again, so to save time, so you can try this. Once we do one, I think it's good, right? So for the other one, the concept, right, basic idea is the same. The only difference here is what? You rationalize the denominator instead of a numerator, right? Here, because this is the denominator, right? Rationalize. Why you need to rationalize? Do I have to rationalize? Yes, you have to rationalize. The reason is what? The reason is if you plug in, you get 0 over 0. That's why you need to rationalize. Right? Whenever you plug in, if you get 0 over 0, then you have to do extra work. Right? That's why. So it's always good, right, to check, see what happens. If you plug in directly, see what happens. Right? If possible, that's good. If not, right, if you get 0 over 0, then you do extra work. Right? If you ask, what happens if I plug in, I get 1 over 0, right? 1 over 0. How is a constant, or 2 over 0, or even infinity over 0? Yes, you will get what? You will get infinity, right? You can think of, informally, you can think 1 divided by 0 is infinity, but technically it's not correct because it really means what? It really means if this one approaches 1, this one approaches 0, but never equal to 0, right? So that means the denominator very, very, very small. Numerator just no change. So whole thing will approaches infinity. Yeah. Okay. Informally, it's okay to think, right? Infinity divided by 0 is infinity. 1 divided by 0 is infinity. That's okay. Yeah. So that's pretty much the basic concept, right? So we introduced for the first chapter. Okay, let's do one more. For we set all these rules, right? All these rules works for finite number A and infinity, including infinity. Right? A is a finite real number or infinity. Okay, so if you change to infinity, for A still works. Well, let's do one, right? Let's do one, this one, do this one. Yeah. So the rule is exactly the same, right? So we can do that. So here, definitely we cannot plug in, right? If you plug in, you get infinity over infinity, right? There's also indeterminate form. If you plug in, right? Infinity over infinity. Informally, right? You can think both infinity. Okay. What we're going to do? We're going to do actual work, right? How do we do actual work? You may learn this already in pre-calculus, right? So we do this way, right? We divide numerator and the denominator by the highest power. Highest power of numerator and the denominator, you know, is what? Is x squared, right? X squared. So we divide out x squared. Why? We can see here. We can use the basic rule, right? We can bring this limit symbol inside, right, of each term, inside each term. We can see here, this one approaches 0. Why? You know, graphically, you can easily see, right? Graphically, you can easily see this one approaches 0, or intuitively, this approaches 0, no problem. Because denominator approaches infinity. Numerator is a constant. So this one approaches. Yes. That's why we divide out the highest power. This all becomes 0. So therefore, we can now we get 1. 2 over 1. Yeah. The rule is exactly the same. Right? But as x approaching infinity for rational functions, you will divide out the highest power. Okay, that's the technique. Okay. How about for next? This one we can divide. This time the numerator has a higher power. If you divide by x cubed, I think it's still okay, right? Or you can divide out x squared. Either way is okay. Yeah, okay. Here, you can divide out x squared, the highest power of a denominator only, right? Divide in this case. maybe let me use using the same technique, right? Just divide out the highest power. That's okay. To be consistent, yeah. Even though for this one it's not necessary, okay? Yeah, it's okay. Yeah. So here we can see this one approaches 0. This one approaches 0. Oh, by the way, it's a pro-0 actually positively pro-0, okay? Positive, not negatively approaches 0 because this fraction is still positive, right? Because x approaches positive infinity, not negative infinity. So this fraction is a positive. This fraction is a positive. Yes, approaches 0. That's why it's a positively approaches 0. Means it's a positive number. Right? So now you can see intuitively, right? If one divided or finite number, right, divided by an infinitely small quantity, the limit is what? Infinity, positive infinity. No problem. Yeah, positive infinity. Okay, let's summarize this rule. Okay, put this rule here. Later you may use it. Okay, so this rule we use quite often, right? Let's write here. So the rule, or you can say formula, right? So it's this one. When you take a limit of 1 over x to power r, if x approaches infinity, this always approaches 0. If r is positive. Yeah, let's say x to first power, second power, or even half power, right? So, because denominator just get bigger and bigger, right? The whole thing approaches 0. This rule very useful. You can see here we use this, right? Use this rule. Why this works? You can use a graphical approach, right, to verify this. Okay, so far, any questions? And let's see. We finished, right? Today, we try to cover both continuity and limits. Probably now we can, continuity part a little short, right? So limits part, we're almost done. So there's one more rule, one more theorem for limits we can use to calculate or prove limits sometimes, right? Very useful. I would say it's very likely, right? You will see one problem involving this theorem called the squeeze theorem. This is just another rule because it's very important we separate them. Okay, we separate. So it's called a squeeze theorem. We use it. We can use it to evaluate limits sometimes, right? So what's the idea? Very simple, right? The idea said this. You can read the theorem. Idea is this. If I have a, let me see where I can write. Maybe I can write here, okay? If I have a 3 function, okay? So this is one function, this is another function, and this is another function. Okay, let me use a different color. Better. Okay, let's see, this is middle function is a g, right? And the top blue one is h. And the bottom one is f. You can see the relationship between these three functions. Yes, is this. Right? Near point A. Right? Near this point. Right? Near point A, except possibly at A. We said function value at A doesn't matter, right? You can draw a hole here if you like, right? You can draw a hole here. Doesn't matter, right? Function value at this point doesn't matter. So the squeeze theorem says this: if a function is squeezed or sandwiched by two functions, right? If the two outside functions have the same limit, if they have the same limit, that means what? The middle one has no choice, must have the same limit. That makes sense, right? So as x approaches A, if both function here approaches A, approaches L, then the middle function must also approach L. Intuitively, it makes sense. It's called squeeze theorem. Yeah. So here, this is how our probably now I can define the nature of this course. I think it's better to treat it as a preview, kind of a enrich, get a little bit fast paced, right? Preview course. At the same time, we're going to use, maybe every time we're going to use a little time to review something you learned in school. If you have a question, we can review. Then mostly I will treat this like a preview course, right? We introduce the concept very quickly, so you get a brief, intuitive idea, then you can solve the problems. When it's come to school teaching, then you can feel more comfortable, right? Comfortable with the concept. Okay, regularly I will give you some practice, right? Give you some practice to consolidate, right? So your skill. Of course, you will also need to do some homework. Okay. Okay. So let's do one squeeze, right? Let's do a squeeze theorem. How do I calculate this limit? How do I calculate this limit? You may say easy, right? Easy, I do this way. Right, this is my limit. Works or not? Let me know. Probably not, right? You cannot plug in because 1 divided by 0 is undefined, right? 1 divided by 0 is undefined. No. No. How about this way? I take a limit of x squared because it's a product, right? I take a limit of sine what? I got 0. Yes, this one 0, no problem. How about this one? What happened to this one? This one equals what? If you're not sure, you use the calculator, see what happens. What happened to this one? Anybody can tell what's happened to this limit? Anybody can guess? How about let me just run pick another student, right? How about Gabriel? Gabriel, what do you think this limit?
Hi, I'm Gabriel, but my internet is really slow, so I'm using the same computer with Kevin.
Oh, Kevin. Oh, okay, Kevin. Yeah. Okay. Oh, okay. Oh, yeah. So sorry, I see this. Okay, I see here.
So
go ahead. Yeah. What do you think for this limit?
So is it also 0? Because no, I think it's like D and E or something, maybe.
This is a little tricky one. Anybody else? Yeah, this one actually, if you use a calculator, okay, use a calculator, maybe better use online, let's say decimals, right? Because the resolution is much better. You can see this one actually, when x approaches 0, 1 over x, you can imagine 1 over x can be 1. Can be very, very big, right? But sine what happens? Sine just what? S0 just oscillating up and down indefinitely. So never approaches anything fixed. So this one actually does not exist. That's why. So we cannot use this rule. Why? Because we cannot use the product rule because this one does not exist. If any limit does not exist, remember, we cannot use these rules, right? To be able to use these rules, each function involved must have limit. So we cannot use this rule. Yeah, we cannot use this rule. Be careful. So this one, no, we cannot do this either. Because we cannot use the product rule. Product rule does not. A one, right? Involving one factor function does not exist, right? Limit does not exist. So then what we need to do, of course, you can graphically, right? You can graph this function if it's allowed, right? In the test, if the question, let's say, calculator, right, allowed, that's good. So you can use a calculator to do it. Otherwise, you have to use one. Use algebraic approach. Here we use one squeeze theorem. So very easy. So we can see this function. You know sine, right? Sine is a periodic function. You know amplitude is 1, right? So it doesn't matter sine, right? What happens? Sine is always between 1 and -1, right? So therefore, if you pick a largest value, amplitude 1, so then you get x squared, right? This should be less than x squared. If you pick a -1, you will get bigger than -x squared. That makes sense? Because this basic property, x squared is a positive number. You can multiply both sides of any inequality by a positive number, right? Doesn't matter because then you keep the same direction. Okay, we got this. That's good. Then what? Then we can see because both outside functions approaches 0. Therefore, this symbol in math is the standard, right? So this means because or since, this means therefore or hence, right? By squeeze theorem, right? This equals 0. So by the squeeze theorem. Yeah. Very good example, right? A squeeze theorem. Yeah. Okay. Good example. Last one, I want to introduce a special limit because we use this a lot, right? Very often. So I just introduce here without giving the proof. Proof actually is a very elementary, means what? Use geometry in the unit circle, right? The geometry we can show as x, no, here we use theta, right? Because we treat it as an angle, right? When theta approaches 0, if you compare sine theta and theta, actually they have same speed, right, of approaching 0. So basically the limit of their ratio is 1. If you want to, how do you prove this? We save time, right? We don't give proof. You can read the book, right? Read the textbook. It's a quite a geometric, yeah, elementary geometry using triangles. Just keep in mind, in calculus, whenever we see angles, it's always in radian, okay? So it's not degree, so it's always in radian or real number, right? Theta is a real number. Not in degree. It's a real number, or you can say it's in radian, right? Okay. If you take the ratio, actually equals 1. This formula justifies why radian mode is much more convenient than degree mode in math, especially in calculus. The reason you can see this formula very neat, right? If you use a degree mode, you will not expect 1. You will expect something else. Okay. Okay, very good. So try to memorize this basic limit because we use this a lot, right? We use this a lot. So using this basic limit, there's another 1 or 2 basic limits involving exponential or log functions. Later we can talk about, right? So this one, basic one. You can use a graphing calculator to verify. It's very easy. You can see if you approach 0. If you look at the graph, very easy, right? Using the graphing calculator, you can check. Approach is 1. Yeah, I think the graph looks like this. You can double check, okay? Like this. Yeah, you can see, oh, of course, there's a hole, right? And 0 is undefined, there should be a hole. But if you use the graphing calculator, you will not see this hole because of resolution, right? You don't see that. Okay. Yeah. Let's use this limit to do 1 or 2 example. Okay, using this limit. Okay. I would say this another basic skills, important skill in about limit. Okay. Of course, later you can use the L'Hopital rule, use other method, right, to evaluate this one. But here, I think if you can master this limit, right, using this limit, then you can calculate very quickly. Okay, so this one, again, when you calculate limit algebraically or analytically, you plug in first, right? If you plug in, you get 0/0, indeterminate form. Then you need to do extra work, right? In this case, we can use what? We can use this rule using this basic formula, okay? Basic limit. How? We are going to introduce very important, right? Very important methodology in math or in algebra calculus, right? So is what is called substitution or change of variable. Change of variable. Right? So you treat 3x as a new variable, right? New variable. We want to change to basic limit. Or maybe you can use theta, right? Any letter, fine, right? So what happened to the denominator? Of course, we know x will be what? X will be theta over 3, right? As x approaches 0, of course, theta is also approaching, right? Theta is also approaching 0, no problem. Now we change to variable theta. Right? Okay. You can see this called usually called many textbooks, right? Call this substitution technique or change of variable. Or change of variable. Okay, so get this. Oh, that's good. Now we can see we got what? We got this. Right? You see, we flip, right? The denominator fraction. Get this. Oh, now we can use a basic rule. We can bring out the constant. Then we take a limit of this. Oh, this basic limit we know is 1. Yeah, so we got 3. Similarly, for the other one, right? For this one, you can do the similar approach, right? You can do the similar approach. You can introduce 2 variables, right? 2 variables. So here, introduce. Oh wait, I think in this case, I'm going to do this way, right? Going to do this way. There's no x involved. I can do this way. This is 3x, right? If you don't like introduce variable explicitly, that's okay. You can do this way. You can put a 3x here, right? Times 3x here. This is a 5x. Oh, here we don't want to use 3x, right? We want to use 5x. Yes, 5x. You can see this match the basic pattern, right? This one match the basic pattern. Yes, this is a theta, right? 3x is a theta. This one also match the basic pattern, right? 5x is the new variable. Okay, but if we add 5x, 3x, what happened? We add something which is equivalent to 5/3, right? So I need to multiply 3/5 so that I can get same equivalent expression, right? If I cancel out, I still get original. Everyone can see the trick here, right? That's how we multiply, right? Our expression change to this. Yeah. The key here is what we want to, right? Come up with this kind of a special limit. Yeah. Okay. X approaches 0. If you like, you can introduce a new variable for each here. Right here, 3x equals u. Here, 5x equals u, or v, or theta. Doesn't matter, right? But here, probably you don't have to, right? You just treat 3x as a new variable, right? Mentally. Okay. Of course, 3x approaches 0 also, right? 5x also approaches 0. So therefore, the first one must be 1, right? Second, also 1, because it's reciprocal, right? Of a basic limit, still 1. Oh, this constant we can bring out. Right? Okay, so we got this one. Yeah, that's how we apply this basic limit. Yeah, we see this limit very often. I think it's good to know this one. Later, if you want how to prove or how to derive the derivative of a sine, cosine function, actually is based on this special limit. Okay, that's good. So you can try this one involving a little trig identities. By the way, trig identity is another important, right, algebra skill, right, you need, right, in calculus. Okay, use trig identities. You can change this to this form. It will be helpful. Okay, think about, right, what's the what trig identity can help with this. Okay, good. Okay, very good. So I think today, very quickly, right? So we covered the first topic, right? In chapter 1 is a limit. I would say